All right, we're going to pick up where we left off in section 3.4, which is algorithms for adding and subtracting. And we had gotten to the point where we had looked at addition and subtraction in base 8. All right, so we did this one with base 8, reminding ourselves that there's no 8s or 9s in base 8, right? And so when we had the 7 plus the 4 in the standard algorithm, we had to remember how many 8s this is. So 7 and 4 is 11. How many 8s is that? That's 1 8, so we carried the 1 8 over, and there's 3 left over from that. Okay? And then we added the 1, 3, and 1 to give us 5 in the 8s column. And then we did this one with, and again, it doesn't really make a lot of sense to do it with scratch addition, but just so you could see it and play in another way, we did a scratch addition one. So if you actually add this one, the 4 plus the 7, one way to think about that is, of course, once you get up to 8, you scratch out 8. Just like in base 10, once you get to 10, you scratch out a 10. So when we have 4 plus 7, that's 11. We scratch it because that's bigger than 8. And we take 8 of them away. So 11 minus 8 would be 3 left over. So you had 3, which is where we wrote the 3 down here. And then you count the number of scratches. There's only 1 scratch, so we carried the 1. And then we added the 8s column after that. Okay. And then on this one, we did subtraction, same numbers. But we can't take 7 away from 4, so we borrowed with our standard algorithm. And when you borrow in base 8, you borrow 8. So when we borrowed 8 from the 8's place, we already had 4. 8 and 4 is 12. So there's a 12 written here. It's not a base number. It's just 12 individual units. Okay? So this is 12 then minus 7, which I can do. That's 5. When I borrowed from the 3, I borrowed 1 of them, reducing it by 1 to give me a 2, and 2 minus 1 is 1. And then I showed you what this would look like with equal additions over here. So equal additions, the whole goal is no borrowing is allowed. So if I add 1 to the 1 7 down here, that would become a 2 0 right here. But if I add 1 to the 1 7, I have to add 1 to the 3 4. So it becomes 3 5, and then 3 5 minus 2 0 is 1 5. Equal additions worked really, really nice on that one. Made it really clean. Okay. Any questions on these two? Yes, Elisa.
How did you get the 7 plus?
Why did I choose the 1 to add?
7 plus 1 equaling 20.
It's not 20. It's 2 0.
Okay.
Okay, because it's base 8.
Yeah.
So in base 8, there is no 8. So when I run out of digits in base 10, I have to use the next digit over, right? So what comes after 19? 20. In base 10, right? Well, what comes after 1 7 in base 8? 2 0. So that's what happened. It's the next digit over.
So that's a 17.
It's a 1 7, right. We don't want to say 17 because 17 means 10 and 7 ones. We don't have a 10 and 7 ones. We have an 8 and 7 ones. So we'll say 1 7. Let's try another one with the base 3. Okay, so remember, base 3 only has 3 digits, 0, 1, and 2. All right, no 3s. So we will add with standard algorithm, and then we'll add with lattice so that you can see how that one would look. All right, so this one is 1 2 1 2 plus 1 1 2, and it's all in base 3. So we have 2 plus 2, which would be 4. I mean, it is, it's 4. But that's too big for our base, right? How many 3s are there in the number 4? 1. So I'm going to carry 1 over. How many is left over from the 4 if I carry over a 3? 1. So I'm going to write down the 1 down here. Carried 1 because there's 1 3 and there's 1 left over. Next column I have 1 1 1. That's 3. But that's 1 3 with 0 left over. Then I have 1 2 1, which is 4, which is 1 3 to carry over and 1 left over. And then I have 1 plus 1, which is 2. It's 2 1 0 1 base 3. So let me show it to you with lattice now, okay? So this is 1 2 1 2 1 1 2. The way lattice works, if you'll remember, is you draw a box underneath and you divide it into as many boxes as you have addition facts, add-in values, okay? And then you divide them in half. along the diagonal. Like that. Okay. So it doesn't matter if you move left to right or right to left here. So we'll go left to right just because we can. So if I add 1 to nothing, I get a 1, and the 1 is down in the bottom right-hand box. Here I have 2 plus 1. 2 plus 1 is 3. But the top corner is how many 3s I have. The bottom corner is how many's left over. So I have 1 3 and 0 left over. Another way you can think about it is you can say, okay, I have 3. What is 3 in base 3? Well, the number 3 in base 3 is written as 1 0. Just like the number 10 in base 10 is written 1 0. The number 8 in base 8 is written 1 0. Whatever base you're in, if that's the value, it's written 1 0. All right, the next one is 1 plus 1. That's 2. So that's 2 in the bottom corner. Okay, there's 0, 3s, and 2 left over. And then I have 2 plus 2, which is actually my 4. How many 3s is that? 1 3 with how many left over? 1. Okay, so that's all of the intermediate sort of in-between steps. And then we add along diagonals, and we do need to move now from right to left. We do not have a choice at that point. So bottom right-hand corner, this is a 1. 2 plus 1 is 3. That's too big. So it's 3. I'm going to carry a 1 over. Hang on, let me use the orange. And write down a 0. Carried a 1, wrote down the 0. 1 plus 0 would be 1. And 1 plus 1 is 2. This is 2, 1, 0, 1, base 3. Any questions on that? Okay, let's try another one. This one's subtraction with base 3. Okay, slightly different digits. We're going to do 1, 0, 0, 2, minus 1, 1, 0, and we're in base 3. Okay. Obviously on the right-hand side, the 2 minus the 0 is just fine. That would be a 2. Correct? But these zeros at the top are too small to borrow or to subtract the 1s from. So we have to borrow. And we have to come all the way over here to borrow from this far left-hand placeholder. So when we borrow it, it's going to go away, right? But we're in base 3. So when we borrow in base 3, how many do we borrow? 3. So this one will become a 3. Okay? But I need to keep borrowing to get that other 0 also to change, correct? So when I borrow from this 3, what will it become? A 2. And what will this 0 become? A 3. When I borrow a 3. It decreases the value I'm in by 1, just like in ours. But when I borrow, the amount that I borrow is 3. And then I can subtract. 3 minus 1 would be 2. 2 minus 1 would be 1. And this is base 3. All right, so I'm going to show you equal additions again. So this is 1, 0, 0, 2, and 1, 1, 0. Okay, our goal, remember, in equal additions is no borrowing. Okay, so clearly, again, nothing wrong with the 2 minus 0 part, right? But I can't do the 0 minus 1 part, right? The goal is to make whatever digits you have down here become zeros. And that's it. We're turning things into 0. So what would I have to add to a 1 inside of base 3 to become a 0? 2. I would need to add 2. So I need to add it in the right place value. So since this is the second place value over, I'm actually going to add a 2, 0. Okay? So this 1 here and this 2 here will increase to make that a 0 in that location, and the value to the left of it will actually become 1 bigger. So let's actually do the top part first because it's the easy ones. This is 1, 0, 2, 2, right? And this 0 stays a 0. The 1 in the 3 spot right here will become a 0. That was the whole goal. And then the fact that I have the 2 and the 1, which makes 3, will carry it over to the next place value. So this is now a 2. Okay, so now the 1's place is good. The 3's place is good. The 3 squared's place has problems, correct? I can't do 0 minus 2. What would I have to add to the 2 to get it to become a 0? A 1 in the right place value, the 3rd place over. So this would be adding a 1, 0, 0, so that the 1 and the 2 that are combining will actually become what I want them to become. So this is 1, 1, 2, 2 on top. And what will I get on the bottom? So this 2 will become a 0, and then what will happen? Will be a 1, right? So I actually get the number that looks like our number, 1,000. It's a 1 followed by 3 zeros. Can you subtract from this one pretty easily now? You bet. It's the whole goal, right, is to avoid all the subtraction with borrowing. So this becomes a 1, this becomes a 2, this becomes a 2, and this is in base 3. 1, 2, 2, base 3. Okay. We're going to do some different things now with mental math, and in a minute with estimation, okay? So mental math. This mental math, there's going to be some different processes we're going to look at. The first one's called adding from left to right. And so we're not estimating here, we're not approximating, we're actually finding the value. Just because it says mental doesn't mean that we're getting an approximation. It just means we're doing it in our head. Now, the catch to doing something in your head is that I can't see what's going on in your head. So I want to show you what you're going to write down to show me what's going on in your head, even though like the process for actually writing it down is sort of like a repetitive thing that's not really necessary to do the problem. You guys with me? It's just allowing me to see what you're doing. All right, so here is what mental addition looks like when you do it from left to right. It means looking at this number and adding, for in this case, the 40 and the 30 first. So what is 40 plus 30? Yeah, 70. And then it's adding, what are my other numbers? 6 and 8 next. What is 6 and 8? 14. And they're adding the result of the 40 and the 70 and the 14 together, which gives you 84. See, there's no carrying, right? I didn't actually add 6 and 8 and then carry the 1. I didn't do it that way. I added the tens places together. And this is really what you would do if you were dealing with money, right? You group all your tens together and you say, look, I had 4 tens and 6 ones. Pretend like you don't have any $5 bills. 4 tens, 6 ones. And then you have 3 tens and 8 ones. How many tens do you have? 7 of them. How many ones do you have? 14 of them. How much do you have total? 84 bucks. This is what you would do if you were doing money. It's exactly what you would do. Adding from left to right. All right. Breaking up and bridging. This is the next one. Breaking up and bridging keeps one of the numbers the same, usually the first one, 46, and it only adds the tens value of the second one to it. So you do 46 plus 30, again, almost as easy as doing 40 plus 30, right? I mean, really, it's going to be fine. And then 76. And then you add the remaining part of the one's value to it. So you broke it up. You broke the 38 up into 30 and 8. And you added them to the number 46 one at a time. And then 76 plus 8 is almost like adding just the 6 and the 8 together, really. And then you get your 84. That's breaking up and bridging. Add the tens value first, add the ones value second. Trading off. Trading off feels kind of like equal additions, okay? So here's 46 plus 38. I don't really like adding 38. In fact, if I were adding these, I would never add 38 to the number 46. What's a number close to 38 that would be nice to add to 46? 40. It's exactly 2 more, right? I'd much rather add the number 40 here. But if I add 2 to the 38, I'm going to take away 2 from the 46. See, when we did equal additions, it was with a subtraction problem, right? This is an addition problem. So if I add 2 somewhere and I take 2 somewhere else away, that's equal. I mean, I've done something equally. It's trading off, right? This is kind of like, so when we did equal additions, we talked about the fact that If you add 2 to each number, you know, we all put on 2-inch heels. We're all the same differences in height that we were originally, right? This is the opposite of that, right? This is adding 2 inches to my height, and then I have to take the shoes off and I decrease the 2 inches from my height, something like that. All right, so if I take away 46 minus 2, I get 44, and then I can actually add these together to give me 84. Okay, add 2 one place, take 2 away in the other spot. It's an addition fact. All right, compatible numbers. I use this one when I grocery shop. I use it with estimation, obviously, too, because I'm not really concerned about exact when I get to the register. I'm just going to be trying to get approximate, make sure to overspend my cash in my wallet kind of deal. But compatible numbers is the idea of grouping things together that are easy to add together. For example, the 40 would be most easily added to which of the following numbers? The 60, right? The 40 and the 60 simply go together the best because they add to 100. What other pair of numbers here are nice? The 30 and the 70. So honestly, this problem should look very clearly like the number 250. But if you really added 40 plus 30 plus 50 plus 70 plus 60 in order, that's harder to do, right? This is called compatible numbers, grouping together the things that are most easy to work with together. And we're allowed to do that because addition is what we call commutative, right? Commutative, we can switch the order of things. It's also associative, so we can group things together in different ways. We can make compatible numbers. Now, these two numbers are not compatible. Agreed? I mean, they don't add to 100, basically, like the last set do. But we could change one of them so they did. We could change the 68 into what number? What number would really, really nicely add to 35 to give me 100? 65. Well, that's 3 more that I need to add on at the end. So now I've made these compatible numbers, and I've got the 3 at the end, so I have 103. Okay, so is there a lot of work to write down? No. But can I tell if you've written this little bits of things what you're thinking? Absolutely can. Okay, so there's a little bit of writing involved with mental addition, just so I can see it, not because it really requires you to do the writing. Make sense? Okay, I think there's one more of these. Breaking up and bridging, on this page anyway, subtraction. All right, breaking up and bridging with subtraction, same kind of idea. So we're going to take the 46, and we're going to take away, so we're breaking up the 38 into 30 and 8, okay? And we're going to take away the 30 first. Okay, we're starting with the tens side. So what's 46 minus 30? 16. And then we're going to take that 16 and we're going to subtract off the piece that's left. What's 16 minus 8? 8. So we broke it apart, and we did it in 2 steps. That's breaking up and bridging for subtraction. All right, trading off. We've already done this before. We've done trading off with subtraction. It had another name. It was called equal additions. I write too fast for my screen. That's my problem, just so you know. That's why you see me erase a lot. Equal addition, okay? So again, the whole goal with equal addition is not to borrow. The idea is to create numbers that are easier to work with. So what would I like the 38 to be? Well, I'd like it to be 40, right? So I'd have to add 2 to this to get to be 40. This is a subtraction problem though, right? So if I add 2 to the bottom, I would also add 2 to the top because we're trying to keep the differences equal. 46 plus 2 would be 48. And then I would subtract 48 minus 40 to give me 8. Okay, we've already done that one before. All right, the last one, you've probably used this before, you didn't know it had a name. The idea is to drop the zeros. When you're actually subtracting this problem, you don't really think about the zeros on the end. The question really is about 46 minus 34. So 46 minus 34 would be what? 12. And your answer would be 1200. 100. Because you're really focusing on the 12 as being the values. It's not the answer 12, right? The answer's not 12. We put the zeros back in for the answer, but you ignore the zeros when you're doing the subtraction. And you do that. You ignore them in your head. Okay, now, what happens on the test is that people get really confused between mental addition, which is what we just did, mental addition, subtraction, and then the next part, which is estimation. So please be very careful. Whatever it takes when you get to the test, circle, highlight, whatever. If it says estimate, that's when you're able to do some of these techniques next. If it doesn't say estimate, it means give the exact answer. Okay? So what we're about to do next is we're about to give approximate answers. Our goal is not to be exact. Our goal is to be easy to work with approximately. All right. So front-end estimation. Have we talked about front-end estimation before at all? I don't know for sure. You guys have to tell me. Not in here. Okay. Front-end estimation is the idea that we use just the first value of something and we ignore the rest of it. Okay? So when we're looking at 332, 462, 225, front-end estimation means we only look at the first value of each of them. And in particular, it usually means that it's all the same place value. So these are all hundreds places, right? So we're looking at the 400, the 300, the 200. Okay? So front-end estimation, this part I'm going to do first, means taking each of them and ignoring the tens and the ones places. So this is 300, 400, 200, and we get an approximation, right? This is how many $100 bills we'd have if we were doing this. So how many hundreds is this? 900. Okay? Now, if we were just doing front-end estimation only, we would be done. But this says with adjustment. Okay? So what does adjustment mean? Well, adjustment means looking at what's left and approximating what you've got here. Now, if you look at what's left here, I've got 32 and 62 and 25. Do you see anything that's like almost compatible numbers? Yeah, 32 and 62 is almost what? It's about 100, right? This is about 100. So this adjustment is about compatible numbers. Front-end estimation is just using the first digits. The adjustment is about compatible numbers. And we're not going to ignore the 25. We're just going to throw him on in the end. So now we've got the 900, the 100, and the 25. So what's 900, 125? 1,025. And that's our approximation. That's those squiggly values in front of there. Approximately what this value equals. Did not ask us to find it exactly. It asked for an estimation. Okay?
Are we ever going to have a time when we'll have like 1,000 and then like 100 and like 500?
Not when they're asking you to do with estimation like this. Yeah. The methods usually, in fact, what I have done before, I don't know if I'll do it this way before, is that I usually tell you to choose an estimation technique that makes sense. So if you were given something like that, that wouldn't be an estimation technique that would make sense for that. Okay? All right, grouping to nice numbers, okay? So we talked about compatible numbers before, numbers that really do sort of like combine together to give you 100, right? The same thing's true for these grouping with nice numbers. Our goal is to sort of group a couple of them together that are about 100, okay? So we want to go through the list and kind of decide which of them we might like to group together. And you may not choose the exact same ones as somebody else, and that's okay. There may be more than one choice that makes reasonable sense. So somebody give me a pair of numbers that seems reasonable to combine.
35 and 55.
35 and 55. Those are about 100, right? They're close. What else?
42 to 60.
The 42 and the 64 are about 100, right? And this one sort of gets left out. That's okay. So we'll approximate him. We can at least talk him, say he's 70. I mean, there's no reason to call him 71. We're not trying to be that precise. This would be about what then? It's about 270. And just to give you some kind of idea, this is not the grouping that I did on my paper. My grouping on my paper gave me an answer that was about 250. That's okay. All right? When I grouped on my paper, I grouped the 42 and the 64 together, but I grouped the 35 and the 71 as being about 100. It's also about 100, right? Yeah, it is. It's a little over. Yours is a little under. It's okay. It's all good. Okay, we're all good? Okay, so this would be grouping to nice numbers. They're not quite compatible, but they're awfully nice to group them in some way.
When we do these on our homework,
work. Yep. Clustering. Okay, clustering is another example where when it works, it's fantastic, but it doesn't always work, right? Kind of like the one that Lauren was asking about. Clustering means that all the numbers are really kind of close to the same value. What value are all these numbers pretty close to? They're about close to 500, aren't they? Yeah, they are. So this is really like the number 500 added together how many times? 5, right? So what's 500 added to itself 5 times or multiplied by 5? Yeah, this is 2,500. Is that good? When it works, it's fabulous. All right, we're going to do rounding next. Now, rounding, with what we're doing here, doesn't tell us like round to the nearest something. We're the ones who are making that call, okay? So we want to be reasonable about it. We don't want to be sort of way off in left field. But when we're doing the rounding, we get to make the decision. So we could say, for instance, that we want to round to the nearest thousands. That would make sense here, right? We've got something in the thousands. So if I rounded this to the thousands, it means rounding the original values. It does you no good to add the two values together and round at the end. That is a complete waste of everybody's time. Because you've done all the work and then you've given an answer that's less precise than you had to begin with. You guys with me? Sometimes I have students who'll try to do that to me. Like, you did all the work. Why would I give you an answer then that's an approximation when you did all the work? The goal in all of these is to do something to make the work less, not to do all of the work. So if I have 4,789 and I round that to the thousands place, what do I get? 5,000, right? I look at the number in the hundreds place, which is a 7. That 7 tells me that I round the thousands place up to a 5. And then I would look at the 3,148, and how would that one be rounded? That would be 3,000. Again, that 1 tells me that I'm going to round down, which just means leaving the 3 where it is and turning everything else into zeros. Yes, ma'am? No, I'm just indicating it so that you guys can see. Yeah. All right, and add these together, and what do I get? 8,000. Okay, now let's do it with the hundreds just so we can see that if you had chosen to do the hundreds place, that would be totally fine as well. This one doesn't tell us what to round, so we get to pick. So let's say, for some reason, we decided hundreds made more sense with the data we were using or something like that, or we just weren't sure that's the one we picked. All right, 4,789 means that I would look at the 8 to make the decision. What would that number become? 4,800, right? The 7 in the hundreds place would round up to an 8. 3,148, this 4 would tell me that what happens? The 1 stays, and then I round the others back down to 0. So this would be 3,100, right? I add these together, what do I get? 7,900. Are the answers close? Yeah, they should be. I mean, they should be relatively close. Okay, we got one left. You ready for it? I don't think you've probably seen this one as frequently. This is called using the range. Now, I know you've heard the word range before. So, where have you heard the word range before? In algebra, when you use an algebra word, how do you use it? Do you remember? Yeah. The x's and y's. Okay, so domain is the x's, the range is the y's. Yep, so we use it with graphs. Where else maybe have you heard it before? Some of you have taken it. Mean, median, mode, we've got range, standard deviation, all of those. So if you've done a little bit of probability, if you've taken the proportional statistical reasoning course, we talk about range in there as well. Okay. This is similar to both of those, has the same kind of idea to it. Range means giving a range of values where the answer could lie. So what does it mean? Well, it means taking the values and rounding them both down to their smallest possible thing that you could round to, and rounding them both up to the biggest thing they could round to, and then giving the answer as a range of values. So for instance, if I took 370 and I rounded it down, what would it round down to? 300. And if I rounded 647 down, what would it round down to? 600. And if I add these together, I get 900. Now let's take 370 and round it up. What would I get? 400. And I take 647 and round it up. 700. So 700 and 400 added together give me 1100. And then what we would say is that the range is from 900 to 1100. And in some sense, that's a pretty reasonable answer, right? That means when I go to buy that washer and dryer, or whatever this is supposed to be representing, I need to have somewhere between $900 and $1,100, right? If I get to the register and it rings up $12.50, I know I should be alerted that something went wrong, because my answer should be between $900 and $1,100, okay? And that's the range.